Okay, let's get started. So everyone's here. How about I not record today, give you 20 of the final exam answers, and then and we'll just say that none of that actually happened to anyone else. Yeah. So what is Friday?
The
Supplement. Is it required or optional?
option.
Optional. Okay. Any questions about that, or anything else really? Okay, so any questions on assignment 8 that I posted 5 minutes ago?
No. I haven't got a chance to look at it.
Okay.
What is it about?
Okay, so in case you're not refreshing the page literally every 10 seconds for the past 3 months, here is assignment 8. So great thing is, assignment 8, no test cases at all. Another great thing about assignment 8 is you can pretty much do whatever you want. So what you're going to be doing for assignment 8 is, so you'll be looking at any one of the 7 previous assignments and then adding features onto it. So you can look at the solutions from the previous assignments or ignore them completely if you want to. And what you'll do is you're going to add some cool features onto them. And these can be up to you. I give a ton of ideas in here. But I want you to be creative about this, to put in some cool features that make the program actually really usable and you can show your friends and family and whatnot. And so what I'm going to have you do is, it should have some amount of effort. So like an assignment worth amount of effort. Not like an entire semester project or like a one-day hack or something, but it's somewhere in the middle between those two. If you're going to be using improvements or new features, you should be adding stuff that we learned in the class. So like the first assignment, which was, if you remember, about these 2 cylinders, like a player and an obstacle, and seeing whether they overlap or not. What you probably won't be doing is just adding like 2 players and then checking if any of them collide. What you might be doing is generate a whole bunch of random obstacles, like say 10,000 of them, and look at some properties, like how many of them are overlapping, or if we have some goal that the player needs to reach, is there a way for the player to go without colliding with any of the obstacles along the way? So something that's actually useful and cool and using some of the concepts that you learned. But also, you should be using at least one feature we did not cover in class, because when or if you're going to be programming in the real world, you're not going to know everything. So even the creators of C++ don't know all the libraries in C++. So when you want to actually have something that is really useful and you don't want to have to code it yourself, see if some other library has done it, or see if some feature in the standard library can help you. So I mentioned one example on assignment 6, this standard map, where you can have a key and value pair. So that would be an example of a feature that we did not cover in class. So something like that, using something that you're able to look out there and see what other libraries are doing or what other data structures you could be using instead of just like a flat vector or something. So be creative here. I'm not limiting you to anything. There's no test cases at all, and you can use any assignment. So you just pick one assignment and then you add features onto that one thing. And you can use the previous solutions if you want. You can start from scratch if you want. Yeah, and if there's something on that is not on the list that I provided here, then let me know, and then we can discuss whether that's appropriate amount of work to do, whether it's too much or too little. So you can be as creative as you want on this, or you can just use one of these on here. Yeah, so I just posted it. Please take a look at it. Any questions about it, though? I was supposed to post it in a week, but I posted it today so that you can get a start on it. No questions? Okay, so let's go back to search and sort. My mistake last time about teaching the wrong sort. Let's start over. Well, we kind of know bubble sort, so that's not an issue. So what is the, can any of you give me a high level idea of what bubble sort actually does? Yeah.
Keep switching different indices until the entire thing's in order.
Yeah, it switches indices. So like if I swap two things in adjacent places, why am I swapping them? Because they're out of order. So I'm making incremental progress toward a sorted list. So if there's something out of order, I'm going to move the things that are out of order one place closer to wherever they need to be. Yeah, so you compare adjacent elements all the way through. If there is a swap that's needed to take place at any point, then you're going to go back through with another pass. If you make any pass without ever making a swap, you know the list is sorted at that point. So we did an example of this. So 17 and 23 are okay, but 23 and 5 are not okay because they're in the wrong order. So we swap them. The 23 and 11 now are in the wrong order, so swap them. And then now we've made one pass through the array. Since we did make a swap, we're going to make another pass through. So the 17 and 5 are not okay, so we swap. 17 and 11 are not okay, so swap. 17 and 23 are okay, so we don't make a swap there. But we made a swap along the way, so we make another pass. And with the list that we currently have now, the list is sorted, so we're not going to make any swaps. So therefore, we're done after that pass. Okay, so it's easy to implement. We talked about how to implement it, and I just posted the code about how to actually do that. But the issue is that it's inefficient because if you have one element that needs to go way far away, like if it's a very small element but it's near the end of the array, it needs to go to the front. Each iteration of the passing, you're only going to move it one position closer every single time. So for large arrays, this is actually pretty slow. So selection sort is a step toward reducing the number of swaps. So the idea here is we're going to keep a sorted list at the beginning, and then we're going to find the smallest element that is not currently in what we've already sorted yet. So let's just do an example here. So in this list right here, do we know that 11 is supposed to go at the front here? Should 11 go at the front? Well, we know that's true, but could it go in the front? Possibly. Yeah, it could. But we don't know that for sure. So what we're going to do is we're going to find the smallest element that is not in our currently sorted list. Well, we don't have anything sorted yet. So in effect, we're looking for the smallest element. So what is the smallest element here? 2. So what we're going to do is we're going to swap with whatever is at index 0, the front, whatever's there, swap it with the 2 wherever it is. They just happen to be next to each other here. But if the 2 was instead at the end, we would swap wherever the smallest element is with index 0. And then so the reasoning behind that is, well, if the element here is larger than element 2, then you're making some kind of progress to wherever it needs to go by moving the big element at the front to possibly wherever it needs to go. But you're definitely making progress by putting the smallest element definitely where it needs to go, because the 2 in the sorted list has to go at the front. because it has to be, that's where the smallest element has to be. So right now, how many elements do we have sorted in our list? Do we know definitely are in the right place? 1, which is only the 2. The 3 might be in the right place. The 11 might be in the right place. So is the 29, but we don't know for sure. The 2 we definitely know is in the right place. So then what we say is ignore the 2 at the front. Find the smallest element among the other 3 elements, which is what in this case? Just the last 3, which is the element 3. So that is the smallest element, and swap it with the next index that is not currently sorted. So index 0, is it sorted or not sorted? It is sorted. We assume that it is. So the next index that is not sorted is what? Index 1. The next index not in our sorted list so far. There's only one element in the sorted list, which is the 2 right here. The next element we don't know for certain is in the right place is the 11, which is index 1. So we're going to swap the 11 and the 3. Because 3 is the smallest element among the other ones, not currently sorted. So the 3 has to go at index 1, no matter what. The 11 might need to go wherever we swapped it with, but we don't know that for sure. But the 3 has to go in index 1 here. So at this point, the 2 elements at the front are definitely in the right order, or absolutely in the right order. But we don't know about the other 2. So we look for the smallest element among the last 2, which is what in this case? 11. So then we swap it with wherever it needs to go. What is the next index not in the sorted list? Index 2. So whatever's at index 2, which is 29 here, we swap 11 with that place. So because we know 11 has to go at index 2, and 29 will be swapped to the other place. Well, so then now we know the 3 elements here are sorted. Find the smallest element among the 1 element at the end, which is what? 29. Swap it with itself because it has to go in that place. So in fact, you can just ignore that because 1 element is always sorted. So that's not an issue. But now we have the list and sorted. So we're making incremental progress toward a solution, toward a sorted list, because we're finding the smallest element among the other things and then placing it where it needs to go. I don't know where the other element needs to go, but I'm moving it somewhere else. But I'm definitely placing the thing that needs to go there when it needs to go there. So the 2 is placed first. Then we look for the smallest element other than the 2, which is 3. Once we have 2 and 3 fixed, we find the smallest element among the other ones, which was 11, and then 29. Any questions about selection? Okay, so it's more efficient than bubble sort because, in the sense that we're making fewer swaps. Because for each of the elements to be placed wherever it needs to go, how many swaps are we doing? Just 1, right? All we're doing is finding the minimum element among the other things and then doing 1 giant swap with wherever the smallest element needs to go. Whereas for bubble sort, could we do way more than 1 per element? Yeah, so selection sort is faster, or is more efficient in that sense. But it may not be actually faster than bubble sort. Why? Well, think about, yeah, go ahead. Yeah, well, think about what selection sort is, happens. Suppose that the list is already in sorted order. How many passes will bubble sort do on an already sorted list?
1.
Exactly 1. What about selection sort? Regardless of what the elements are, it will find the smallest element among all the other elements then we'll find, oh, we don't have to do any swaps, so that's good. But I still have to take the time to search through the rest of the list to find the smallest element. I don't know if it's sorted initially. I don't know if, say if the elements are 1, 2, 3, 4, 5. I don't know if 1 at the beginning is the smallest element. I don't know that because I'm given an arbitrary list. So I do have to search the entire list to find whether or not 1 is the smallest element or not. Whereas for bubble sort, I make exactly 1 pass. So for some lists, one type of sort is better than another. So one of the things actually on assignment 8 is actually figure out what lists is bubble sort faster and which one does selection sort run faster. Or what about other sorting algorithms, like the standard one in the standard library? How does that compare to these? Are there some lists that bubble sort is faster than the standard sort? So lots of things to actually take into consideration. Theoretical, we can make an analysis of how many swaps we might do versus how does it actually perform in practice. Yeah, so you can call the sort function because that's pretty much always faster than bubble or selection sort, but do we know that that's always true? No, so you have to profile and run your program and to see whether which sort is actually faster. Any questions on sorts? Collection of sorts. All right, so we actually started talking about this, so I'm gonna go a little quickly through it so that we can get to the interesting stuff on this. So if we do want to make a comparison, say, between bubble and selection sort, which one is actually better, then we need to analyze the actual algorithms. So we can make different measurements we can look at. Like, in addition to the list that were provided, what additional memory are we using? And we found that bubble and selection sort actually don't use a lot of memory in addition, like 3 or 4 integers or something. Very small compared to an arbitrarily big list. So if I feed you a 10 million element list, which is actually not that big in practice, but 10 million elements compared to a 3 or 4 integer overhead, that's actually quite small comparatively. So you have to actually figure out, by looking at the algorithm, how much overhead am I actually doing here? How much space am I actually using? How much time am I actually using? Things like that. So we're going to actually talk about this in a general context, but just note that you can make this analysis for time, how long it takes, or how much memory it actually takes. Yeah. And it's more effective than just using just raw data. You could say, well, I ran it on this 100 element list and it took this long. Therefore, for a 10,000 element list, it'll take this long. Is that necessarily true? No, not necessarily. So analysis of algorithms is abstracting away from the details about like specific sizes of lists or input or whatever, and then just talking about the runtime or anything in a general context, which is a lot easier. So we talked about this type of these definitions here, but basically we're going to be looking at this thing called a basic step, which is not really precise, but it's just something that you can't really make, you can't subdivide it into smaller things. So like adding an integer to another one, you can't really break that up into smaller pieces. But like, or comparing 2 values, for example, you can't really break that up into smaller pieces. But finding the largest element in an array, well, that's composed of multiple basic steps because I look at the first value, is it the largest I've seen so far? If it is, update. Then look at the second element, then the third, then the fourth, all the way through. So that's composed of multiple basic steps. And so let me ask you this. Are all basic steps going to take the same amount of runtime? So like adding 2 integers, is that going to take the same amount of time as like comparing 2 values? Not necessarily. So, in fact, one of the interesting things is that the same operation can actually take two different times depending on the context. So just be a little bit careful here when you see this. Like, you see an algorithm takes like 2 times whatever time. That's not necessarily true because some operations can take longer than others. And it depends on the hardware for how long it actually takes. But we're just going to look at it from a general context. Get rid of all the details. Just look at it from a high level. Any questions about terminology stuff? Okay, so more terminology, great. The way that we look at saying this algorithm is better than this one, or worse than another, or the same, is we look at something called the complexity of the algorithm. So this could either be the time complexity, so how long it takes, or the space complexity, how much memory does it take, or memory complexity for that matter. So we're going to be, again, abstracting the details away, and we're going to be looking at inputs of size n. So you can think of this as a list with n elements in it. So if I feed you a 10 million element list, then n is what? 10 million, yeah. So we're looking at it from a general context, an arbitrary n, not just a specific value of n, like 10 million or 10 or whatever. We're just looking at how does the algorithm behave if I feed you longer and longer and longer and longer inputs. So think about say linear search. So if I feed you a list of size n and it takes some amount of time, what should you expect on average the time it takes to do linear search on a 2 times n length list, so twice as long? How long should you expect the runtime to be? Twice as long. Because on average, we're searching linearly through the list. So if the list is twice as long, we should expect to take about twice as long to search through the list. So again, that depends on what contents are in the list. If I find elements near the beginning at all times, then that might change if I look at a twice as long element list, because I may have different contents in the list. But on average, I should take twice as long. So we often look at 2 different types of complexities. So what does it do in the worst possible input? So think of me or whoever you want as a devil's advocate. And I'm trying to make your algorithm run as slow as I possibly can. So the worst case complexity is, if I were to feed you that list, how long does the algorithm take? So think about linear search again. So what is the worst possible scenario for a linear search? That is the last element, or maybe not even in the list. So either of those is okay. So what is the worst case complexity of that case? So if I have n elements, how many might I compare in the worst case? Or look at in the worst case? N, or n minus 1. So, but roughly n, right? What about average? If I have an arbitrary list, what is the average number of elements I might want to look at? I might need to look at? About half, right? Because I could find things at the front, or things at the end, or things in the middle. On average, it's about half. So we often look at worst case complexity because I only need to show you one example that makes this run as slow as possible. But for average case, I need to look at every possible list that I could ever give you and any value that I could ever give you and analyze all of those cases. So that's actually quite difficult to do. So worst case is often the choice for understanding algorithms. But for average case, it's obviously better to analyze average case because that affects real world performance. On average, how long should it take? But what is another nice thing about worst case? it's a guarantee. If I look at the worst case, could it run slower than that worst case? No, so it's actually a nice guarantee. So we're going to look at the worst case complexity. So let's look at this example. So this is basically finding the largest element in an array. It's not actual C++, so it's written more in English, but you can translate it into C++ if you want to. So we're looking at the biggest element. It could be the index 0 thing, or it might not. And then what we're going to do is we're going to iterate through the array or vector, and we'll check at each element. If this element is bigger than the one that we're maintaining, then update the biggest one that we've seen. And so by going through the array like this, we'll keep track of the largest element that we've seen. And once we go through the entire thing, we now know what the largest element is. By the way, did anyone see what the errors are here? So this is not my code, but it's from the publisher. So what should this be? Should this be A of n? What is the observed element? Index. Yeah, should be index here. What about here? It should also be the same. Does index ever change in this loop? Where? No. So this could be an infinite loop. So please implement this correctly. I posted code about linear search, so you should be able to implement it correctly. But imagine that those things are there so that this code is correct. Well, how many times do I do these first two lines, only these two lines? Exactly once. So you can think of them as one basic operation each, or one basic step each. Well, ignore the loop for a second, the outer while loop part. Just the code on the inside, the four things in here. How many basic steps does this take? Just the four things on the inside only. Well, how many basic steps is the if statement? It's between 0 and 2. 1. So it's only one step to compare two things because I can't make that any better. What about setting the biggest element right here? Just one. So 2 steps essentially. But how many times am I going to do that? N times, because I'm going to be checking n elements, right? So that means the number of basic steps in this case is 2 for the inner part times n, which is the number of times we're going through, plus 2 up here. But that's actually not quite correct. Yeah.
Is the comparison while loop also?
You mean the if statement in here? That's inside the while loop.
No, the while one. Is that on one time?
Oh, good point. Yes. So that's also true. So the comparison in the while loop is also a thing that we need to consider. So in fact, for each of them, there are 3 times n plus 2 at the front. But is that true? What if the biggest element is at the front? So we find it so we set it up here. Will this if statement right here ever be true? No. So then in that case, will this biggest equal a n line, or a of index it should be? Will that ever be executed if the biggest element's at the front? No. So what should we say about the runtime when I said 3n plus 2? What is that? Is that the worst case runtime or the average? The worst case. In the worst case, I do every single step in here every single time. But depending on the list, I may do fewer. So that's why worst case is so much easier to analyze, because just look at the steps and just count them. And so that's much easier. Any questions on the example? Okay. Yeah. So so let's just say that we are comparing bubble sort and selection sort. Actually, let's do linear and binary search for now, because this is a good exercise. Don't want to show you research stuff. Let's actually do linear search and binary search. So again, this is in the worst case. So what is the worst case for linear search? Yeah, like the number of basic steps. So again, this is really nice about analyzing algorithms. I don't care whether it's like 2 times n or 3 times n or 10 trillion times n. Ignore the constant on the front, the number. Is it n or something less than n? It should be n, right? So I may have to look at all n elements for linear search. So n. So let's just say the list has n elements. What about binary search? Well, let's see. We're cutting the list in half every single iteration. So we're dividing the list by 2, then 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 by 2, until we get to some point where we have some other condition where the 2 pointers go in the wrong order. But ignore what that does. Does anyone know how many steps in the worst case binary search does? Well, let's see. Look at the very end, right before we say either we found the element in the worst case or we stopped because we couldn't find it. Well, look at the size of that list. Then reverse the algorithm. So instead of dividing the list by 2, we're expanding the list, multiply it by 2. So whatever it is at the end, multiply it by 2, multiply it by 2, multiply it by 2, multiply it by 2, etc., until we get back to the original list. So let's see. Well, we don't know necessarily how many times we divide the list by 2 every time. But how many elements do we end up at? N. So we're multiplying by 2 some number of times until we get to n. Well, let's just say that we take k times. We divided the list k times, and now we're expanding the list back k times. If I multiply 2 by 2 by 2 by 2, etc., k times, how do I write that? 2 to the k, right? So 2 to the k, whatever that is, equals, well, if we expanded that list until we got to the original list, how many did the original list have? N. So we have now this equation to solve. And if you solve it, it's log n base 2. So the number of things that we need to look at in the list is, in the worst case, log of n base 2. So I just did this in my head. If you have 1,000,000 elements in your list, in the worst case, 1,000,000 base 2, the log of 1,000,000 base 2 is around 20. Whereas for linear search in the worst case, I may have to look at 1,000,000 elements. So what is better, 1,000,000 or 20 for looking at elements? 20 is way better. Yeah.
So you don't have to look at 2 to the k unless you only care about how many times you do it.
So the k here means the number of things I'm going to be looking at in binary search. If I'm going to be looking at 2 to the k of them, that's effectively looking at the entire list anyway. So it's just solving this equation for where k is the number of things we're looking at. So now that we did that, let's look at this slide right here. So it says that we have complexity functions f of n and g of n. So in our example, let's say that n, so I'm going to put this back here to make it easier to read. So I'm going to have f of n be n and g of n be log of n base 2. Is there a way that I can make this better? Okay, so let's just say that we have that case. So we want to compare, is linear search better or binary search better in this sense? N versus log n, Which one's smaller? As n gets big. If you have like really big lists, is n better or log of n better? Log of n, because it's way smaller. But so let's actually look at this. So let's look at the ratio n over log n. So if you break out your calculus, but you don't actually have to here. If you look at n over log n and just make n go big, as big as you want, does that approach a constant number? So if I have like 1,000,000 over 20, and I make 1,000,000 bigger and 20 slightly bigger because of the log, is that going to approach some number, or is it just going to keep going up and up and up? It's just going to keep going up. What if instead binary search just happened to have a runtime of 2 times n? Is the ratio of f of n over g of n approaching a number, just a fixed number? Yeah, 1/2 in this case. So in this case, n and 2 times n, are these equivalent efficiency? According to this, yes. In reality, which one should you use? The n one, because 2 times n is bigger. But from an efficiency point of view, in this sense, are they equivalent? Yeah, because if you look at n over 2 times n, what does that simplify to? 1/2. So does this number depend on what n is? No. If I make my list bigger, the ratio between the two algorithms is the same. Even though their absolute difference is going to keep going up, the relative difference stays the same. But look at this now. So let's revert it back to log n. These are not equivalent because n over log n, the relative difference is going to keep going up. It's not going to stay the same. Yeah.
Why does relative difference matter? Because you're still going to pick one.
Yeah. So the reason why we look at relative difference is that it's way harder to analyze absolute difference. If I want to know the exact difference between these two algorithms, then I need to know precisely the number of iterations that are going to take place, the number of basic steps that are going to take place. Because if I don't know that exact number, I don't know the absolute difference anymore. So linear search, well, that I don't know how long that's going to take in general because I need to know the list in advance in order to know how long it'll take. But in the worst case, I do know what that is. For binary search, I don't know what it is in general, but we look at it from a worst case point of view. So by doing that, we need to look at this from an efficiency point of view because if I have like, even if the worst case is like 2 times n or something, then if I'm looking at a trillion element list, a trillion versus 2 trillion, it's not going to really matter that much. I'm still going to spend a whole load of time trying to process this list. So the way that we analyze algorithms is by stripping off all of the unnecessary details. The n is what is important here, not the other terms in front of it or behind it. But you're absolutely right. If I wanted to really compare these two, I do need to know the exact runtimes here. And how do I know the exact runtimes? Substitute a value n, but what if I wanted to know the exact number of seconds each algorithm takes? What would I do? Implement it and time it yourself. So there's a gap between what you analyze versus what actually happens in practice. So we're just trying to simplify things, ignore all of the unnecessary details here, trying to abstract away. Okay, so let's actually look at, so they're not efficient because n is going to get much bigger than log n. But what about this one? So which one is going to grow much faster? Is the n going to go much faster or log n going to grow faster? The n's going to grow faster because it's it's shaped like this, and the log n is shaped like this. It goes flat very quickly. So, which one is better, more efficient? Is f of n more efficient or g of n more efficient? G of n. So that's what we say here. So if this quantity gets bigger, then g of n's better. If it's the other way, that this ratio goes to 0, it doesn't go to a fixed number, but it keeps going smaller and smaller, closer to 0, then that means g of n is slower because it's dominating the f term. So if I swap these around and I looked at it like this, if I looked at log n on the top and n on the bottom, which one's going to grow faster, the n or the log n? The n. So that means that the denominator is going to keep growing bigger and bigger and bigger comparatively to the numerator, which means it's going to go smaller and smaller and smaller really fast. So by doing this, by looking at this ratio, we can, in some sense, compare one algorithm versus another. Any questions on what that does? So I actually invite you to look at bubble and selection sort, because it's actually really interesting, the worst case runtime and how to compare them there. Okay, so I'm only going to briefly talk about this, but so this is more of an advanced concept, but you see this all over the place and people misuse it like crazy. So I felt it's kind of important to introduce this anyway. So what is this big O thing? Big O means that, so if you say that f of n is big O of g of n, intuitively what that means is that f of n is better than g of n. So in the previous slide where we talked about like which one was better than the other one, then if we looked at the ratio f over g here, then what happens in this case is that the ratio is not going to go up and up and up. So if we look at f of n over g of n in this case, then if this keeps going up, then what is true? Is f of n bigger or is g of n getting bigger if it keeps going up? F of n is getting bigger. So that won't happen with big O. So what big O means is that the ratio, it either approaches a fixed value or 0. So big O is just a combination of they are the same or f of n is better. So it's either that they're exactly the same efficiency or f of n is better. Yeah.
But I thought it will only be better for constant is less than 1.
Yeah, so I'm not talking about the constants here. So there's a lot of mathematics behind what big O precisely means. We're not going to get into that. All it means is that, for our purposes, is that f of n is at least as good as g of n, either the same or better. That's all you need to know about big O. The big O notation just means it means all functions that are the same or better than the one that you passed in. So if we look at the example from linear and binary search, is log n big O of n? So look at this. Is log n at least as good as n? Yeah, so log n is big O of n. What about the other way? Is n big O log n? No, because n is worse than log n. Okay? What about is 2 times n big O of n? Are these the same efficiency from an efficiency point of view? Yes, because we just strip off all the unnecessary stuff. So 2 times n is in fact big O of n. So the answer is yes here, no here, yes here.
You see it as like the inequalities.
What's sorry?
Can you view like the big O as an inequality sign?
Yeah. So in fact, you could view the big O as an inequality, less than or equal to. Yeah, that's one way to look at it.
Or like as you say, wouldn't it be less than or equal to 1? Because if it's greater than 1, it's like the top one's not really efficient. Like in the 2n over n case.
So okay, 2n case, what about it?
So in 2n over n, it's equal to 2, right?
Yeah.
And that means that
It
it's actually more efficient.
So as long as it approaches some fixed number, we don't care. So as long as it's some fixed number, we don't actually care. But you're right. From a real point of view, 2 times n is worse than n. You're absolutely right. But from an efficiency point of view, ignore all of the constants. Just focus on the main thing, the main event here, which is just n, ignoring the 2 out front. What about like n squared? So is n big O of n squared? Which one's going to get faster, bigger and bigger, n or n squared? N squared. So is this true? Yes. So that'd be yes. So it's like one function is better than another. Any questions on big O? So I would only ask like one question on the final about it. So it's not a big deal. Okay, so I'm gonna very briefly start the next chapter. So see the emoji here. What we've been talking about so far is part of the real world. So how many of you have looked at C++ code all over the place and have seen a star notation when it's not meant to use multiplication? But like in a parameter list, for example, you see like int star, for example. How many of you have seen that? Yeah, so a few of you have. That's something called a pointer. So obviously I just pointed at the screen. So what that is something that's really important, but it's not really a good thing to actually start using because of all the pitfalls that could happen. I'll talk about ways to avoid those pitfalls near the end of this set of slides. But I want to actually show you what a pointer actually is and how it's actually used so that when you actually see code where they have pointers in them, you know, okay, this is a pointer. Now I know what is actually going on here. But I'm recommending that you don't use pointers yourself. In fact, in all of my research when using C++, I have not used a single pointer myself. Not one. Because it's just not necessary for what I do. But it sometimes is. So what is a pointer? So what we have talked about for pretty much the entire semester is we have variables, and they're stored in main memory somewhere. So they're stored at some place in memory, some address in memory. So when we talked about references before, which is the ampersand thing, we're actually just passing along that address along. So we're just passing the address along and saying, if you want to actually look up the stuff of this variable, it's at this place. So instead of passing the entire object around, so like a giant vector or something, we're just passing the start of it over so that we don't have to make an unnecessary copy, but also we know exactly where that vector starts. So that's what the reference is. It's just the address. So the address itself, the literal number that represents where the variable is located, that is a pointer. Okay? The address of a memory location, so like this num right here, if we print the address itself is a pointer, not the variable. The address itself is a pointer. And a pointer variable is a variable that holds an address. That's all it is. So we'll talk about pointers next time.